Differentiating under the integral sign is a powerful integration technique used to evaluate definite integrals when standard integration methods such as integration by parts or U substitution are unsuitable. The Leibniz integral rule is eponymously named after its inventor and German mathematician Gottfried Wilhelm Leibniz. It was later popularized by the physicist Richard Feynman in his famous method, Feynman's technique for integration. When a certain definite integral is in this form, whose bounds are some function of parameter x and the integrand contains some variable of integration t, then by deriving this integral we get the Leibniz integral rule. In the special case where the limits of the integral are constants or an infinite interval, the rule can be reduced to a simpler form that only concerns variations of the integrand. Taking the derivative of this with respect to x gives us this integral. Thus, differentiation under the integral sign allows the order of integration and partial differentiation to be interchanged for certain integrals.
Example 1. Find f dash of x and evaluate f of x. So from here we can see that the parameter x is within the integrand as well as the bounds of the integral. So from here we know that we have to use the Leibniz general formula. So first we find the derivative of the integral, and we can use the formula to assist us with this. So we can see that this section corresponds to here with the upper limit, and this corresponds to here with the lower limit, and this one of course corresponds to the integral itself. And so after simplifying these, we get 3 sine x to the power of 5 minus 2 sine x to the power of 4 all over x plus the integral. So now we can take a closer look into this indefinite integral with the partial derivative. So first we will find the partial derivative of sine x squared t over t with respect to x. So we can take the constant out, and then we can apply chain rule, and finally we get 2x times cos x squared t. And now we can sub this back into here to get the integral. Now we need to evaluate this definite integral with respect to dt, and we can do this using u substitution. So we have u is equal to x squared t, and we differentiate u with respect to t, and we rearrange the equation, and we can get dt is 1 over x squared du, and we can sub that into there, and so we get that with cos u, and then we can integrate cos u to get sine u, and we sub x squared back into u to get this, and then we can sub the bounds in to t, and finally we get 2 sine x to the power of 5 minus 2 sine x to the power of 4 all over x, and we can put that back into the equation. So now we can add these two terms up and put it all over one fraction, and finally we get f dash of x is equal to 5 sine x to the power of 5 minus 4 sine x to the power of 4 all over x. Now to find f of x, we need to find the antiderivative of f dash of x. However, this is not actually possible to find the indefinite integral of a function such as sine x on x, as it is not able to be expressed in elementary functions. So therefore we must express it in a non-elementary function such as psi of x, and through u substitution and the use of psi of x, we can arrive at the final answer of f of x is equal to psi x to the power of 5 minus psi x to the power of 4.
Okay, so example 2 here is to show that the integral, which we will define by some function r of x, is actually equal to ln of x, with x being greater than 0. In order to show this is true, we'll be using the special case of Leibniz rule, where either the limits of the integral are constants, are on an infinite interval, which applies to us here. So first we should differentiate the left-hand side, which is I of x, using the Leibniz rule. So basically we want to find I dash of x. And once we simplify as much as possible I dash of x, we can integrate that back into I of x, so we can possibly find if it's equal to ln of x. So solving the equation into this formula, into the rule, we get this. And so we want to start from here now. So here, the integration parts we don't have to worry about. We just care about partially differentiating this with respect to x, meaning the t's are a constant. So our result from this will be e to the power of negative xt dt. And so next, what I need to do is integrate this. Now this is an improper integral, meaning at least one of the endpoints is headed towards infinity. So we need to define t as some parameter of the function e to the power of negative xt. So we have the limit as t approaches infinity. Then we integrate with respect to t, imagining x as our constant. To integrate this, you use the reverse chain rule to get this result. And so our limits are t, with t approaching infinity, and t equals 0. So we bring the negative 1 over x out, as it is a constant. And so for the remaining e to the power of negative xt, as t goes towards positive infinity, we get 0 as the first term. And for the second term, when I sub in t equals 0, we get 1 as the second term, as e to the power of 0 equals 1, which basically equals 1 over x. So what exactly is 1 over x? This is actually I dash x, which is what we wanted from the start. It is the derivative of our original integral. So how do we get I of x equals ln x? Why don't we integrate? So we should probably integrate 1 over x. So we have I x equals the integral of 1 over x dx, which is equal to ln x plus c. However, the problem here is we have a constant. And so we need to match the question here, ln of x. This implies that c should equal to 0. So how do we get that? Well, how about we go to the original integral again and sub x equals 1. What happens when x equals 1? This would actually equal that, and the same term minus each other would actually be 0. So I of 1 is actually 0. And so if we sub x equals 1 here, we have I of 1 equals ln of 1 plus c equals 0. From this result here, we get c equals 0. Therefore, I of x is ln of x, which is what we wanted to prove over here.
The Leibniz integral is predominantly applied in fields related to engineering and physics to measure change involving variation of the interval of integration. Use of the formula is applicable in situations involving much more difficult integrals, hence why it sees most of its use within the fields of engineering and physics. Examples of this are seen in both pure and applied mathematics. A prime example of this is within the field of applied mathematics, specifically in the field of fluid dynamics. Application of rules used to derive an integral that respects the domain in which the fluid is moving over. Time is also another variable. By using this rule, engineers or scientists are able to calculate the change in density or volume of the fluid. Henceforth, the Leibniz rule / Feynman technique can be seen as a powerful tool used to aid the calculation of integrals of high difficulty. Through the examples, we are able to see the process in which it is able to aid mathematicians in solving these harder integrals, therefore furthering our understanding of mathematics.
Okay, thank you very much. So just confirm for me, Catherine, I think you're here. So that I heard Colleen, Brandon, and Helen. Is that correct? Yep. Okay, so we're going to do it. All right. So thank you for that presentation. I'm happy that you've done that. And Rafi, not yet. Rafi, just hop off, mate, please. Oh, okay. No, that's fine. All right. Just wait, please, before you get started. Thank you. Okay. Has anybody got any comments about Catherine's group? I think you were calling yourself Ooh Yeah, or Ooh Yay. Am I saying it correctly? I can't tell.